In the last two videos, we saw how the force production capability of a muscle is going to be a function of what its activation level is, what its length is, and what its velocity is. But generally, from a performance standpoint or a clinical standpoint, we're actually less interested in the force production capabilities of a muscle and more interested in how much torque can we produce at a joint. And I want to venture out into new territory now and start thinking about the difference between the force that a muscle produces and how much torque we're going to get at the joint. So in this case, I'm going to focus specifically on the force produced by the long head of the biceps brachii and the torque at the elbow joint. And for the time being, at least, let's just think of the upper arm as fixed. So we're just going to think about the forearm flexing, the elbow joint flexing, as a consequence of the force applied by the biceps muscle. One of the things that I hope you took away from our first article analysis on bone loss in space is that much of the resistance we face in exercise has to do, or even just in activities of daily living, has to do with the force of gravity. So let's just imagine doing a bicep curl with no dumbbell in your hand at all. Of course, this is a relatively easy exercise to do, but it's not completely effortless. You do need to lift up the weight of your arm. So in a video, I think at the beginning of last week or the week before, I talked about how we could think about gravity as exerting this downward force. Let me just label this as F. Exerting this downward force on objects proportional to their mass. Now, if you've done physics or K391 biomechanics, you know this is going to be mass times acceleration, and in the case of gravity, it happens to be mass times gravity. But that force right here goes down and is going to have the tendency to induce some amount of torque at the elbow joint. So what I mean when I say torque is a tendency of causing something to spin or twist. In the case of the human body, we're always going to be talking about torque in the context of some joint, either extending or flexing, or I suppose in other planes of motion, internally or externally rotating, abducting or adducting. It's just going to be some rotation about some maybe axis of rotation. We could think about the elbow as having an axis of rotation like this, and it just can flex or extend about that axis of rotation. So for the moment, ignoring the muscle, and again, assuming the upper arm here is fixed for the time being, what is the effect of this force of gravity acting on the weight of your upper arm going to be? Let's think about that. So there is a principle I need to introduce called a moment arm. Let me write that out. Moment arm. And it's called this because one of the other words for torque is moment, or even more arcane, moment of force. Because I think you understand the term torque better, I'm going to try to use the term torque as much as possible, but you may encounter the word moment in your clinical or professional life. It means, in the context of torques, it means the same thing. Torque and moment are interchangeable. So the idea of a moment arm is as follows. Some force, in this case gravity, is going to induce some amount of torque at this axis of rotation that we care about, the elbow. And that torque is going to be equal to the product of this force and its moment arm, which if you look up in like a textbook, it will say a moment arm is the perpendicular distance from the line of action of the force to the axis of rotation, which is a totally unhelpful definition because nobody knows what that means. What it means is, from the direction of the force, which is this way, it's whatever offset there is from the axis of rotation. Now, moment arms are really easy to understand in the case of gravitational forces because moment arms are always perpendicular to the force. Maybe I'll just use the math perpendicular to force, math symbol for perpendicular. So because gravity always goes vertically, the moment arm of a gravitational force is always going to be horizontal. So it's always just going to be whatever horizontal distance there is between the force and the axis of rotation. Now, I'm going to introduce the idea of changing this, and maybe label this moment arm. Let's think about what happens when you change the moment arm. Conversationally, the moment arm is roughly equivalent to your conceptual idea of leverage. Sometimes people even use the term lever arm to refer to a moment arm. So do you notice how if I were to grab this force and just move it up here, same amount of force, but just applied further from the axis of rotation, further from the elbow, this would increase the moment arm now to this length, right? So here's the direction of the force. It's going up and down this way. We want to go perpendicular to it to get to the axis of rotation, the thing we're spinning around, which is the elbow joint. So moving the force up to here increased the length of the moment arm. So in other words, this force has more leverage over this axis of rotation. And the formula, it's not a complicated one, but the formula I want to build up to and that you should understand is that torque, the tendency of something to spin, the amount of rotational acceleration you're going to be inducing from some force is going to be equal to the force applied times the moment arm. So one thing you could notice is that if you move this force twice as far away, the same force produces 2 times as much torque. One thing you may have seen before. Let's think about the most common units of force and length you may be familiar with. So maybe feet for a distance. Right? This and the moment arm is literally a physical distance. It's something you could measure with a ruler. So maybe you measure it in feet and you measure force in pounds. If you're familiar with car repair at all, you might see bolts that are labeled with, let's say, maybe 25 foot-pounds. What that means is you should tighten this bolt with no more than this amount of torque. You might also see torque wrenches that are rated for a certain amount of torque in foot-pounds. If you have a car that is not from America, like for example, I drive a Volvo and the bolts on my engine say Newton meters. It's a unit of force multiplied by a unit of distance. So that's the idea of torque. And in the next video, that's the idea of torque and moment arms. And in the next video, I'm going to go through some simple examples of calculating the torque that a particular force will induce. And then we'll introduce more complicated ideas about what to do with the moment arm when the force is not going straight up and down.